Hello everyone, I am Bireshwar Roy. I am currently pursuing my fourth year PhD in the Department of Physics, Indian Institute of Science, Bangalore. In this NPTEL GATE Physics course, I will be discussing some previous year's GATE Physics questions and try to solve them with proper explanations. This question is from the GATE Physics paper 2021. This is a numerical answer type question having 2 marks. The topic of the question is quantum mechanics. The question is, the spin S vector and orbital angular momentum vector, that is L vector, of an atom precedes about the total angular momentum vector, that is J vector. Now, the total angular momentum vector, that is J vector, precedes about an axis fixed by a magnetic field B1 equals to 2B0 along the z-cap direction, where B0 is a constant. Now, the magnetic field is changed to B2 vector, that is another magnetic field vector, equals to B0 times x cap plus root 2 y cap plus z cap. Given the orbital angular momentum quantum number L equals to 2 and spin quantum number S equals to half for the particle. Here theta is the angle between B1 vector and J vector for the largest possible values of total angular momentum quantum number J and its Z component Jz. The value of theta in degree rounded off to the nearest integer is, so we have to find the value of theta here. It is given in the question that orbital angular momentum quantum number L equals to 2 and the spin quantum number S equals to half. So the total angular momentum quantum number J equals to from L plus S to mod of L minus S. So the values of J will be in this range. So the possible values of J will be in the range of 2 plus half to 2 minus half, because here L equals to 2 and S equals to half. So if we just want to find the possible values of J, then it will be in the range of these two quantity, these two number, and the possible values of J will be 5 by 2, 3 by 2. Here the largest value of J equals to 5 by 2. Now for J equals to 5 by 2, the possible eigenvalues of Z component of J, that is Jz, will be Mj equals to from minus J to plus J. So it will be 5 by 2, 3 by 2, half, minus half, minus 3 by 2, minus 5 by 2. Now the magnetic field B1 vector is along Z axis. The angle between the largest value of J and B1 is theta, that is given in the question. Now projection of the J along Z axis is basically gives us the Jz component. So we can write Jz equals to mod of J times cos theta. Now the value of this Z component of total angular momentum vector, that is Mj times h cut, and this value of total angular momentum vector, that will be root over J into J plus 1 times h cut, and here this cos theta is coming due to the projection. So the cos theta is Mj by root over J into J plus 1. What we have is cos theta equals to Mj divided by root over J into J plus 1. Now from the previous slide, we have the value of J equals to 5 by 2 and Mj value equals to 5 by 2. If we put that, we'll get 5 by 2 divided by root over 5 by 2 times 5 by 2 plus 1. So it will give 5 by root over 35, which leads to 0.845. So our theta is cos inverse 0.845, that is 32.31 degree. So this is the angle between the total angular momentum vector J and the magnetic field B1 vector, that is 2B0 z cap. So the angle between largest value of J and B1 vector is 32.31 degree. Now the magnetic field is changed from B1 vector equals to 2 B naught z cap to B2 vector, that is B naught times x cap plus root 2 y cap plus z cap. So basically the magnetic field vector direction has been changed, but the magnitude of the two magnetic fields are same, because it has a magnitude 2 B naught and also the mod of B2 is also 2 B naught. Now the angle between the two magnetic fields given in the question, that is B1 and B2, is phi. So we can write from the dot product formula, that is cos phi equals to B1 dot B2 divided by mod of B1 times mod of B2. So it will be 2 B naught z cap and it will have the dot product with B naught times x cap plus root 2 y cap plus z cap. And the magnitude of the B1 is 2 B naught and magnitude of the B2 is also 2 B naught. So from here we can write cos phi equals to half. So phi will be cos inverse half. So it will give us 60 degree. So basically the B2 vector is making an angle 60 degree with the old magnetic field vector, that is B1 vector. So now our z component of the total angular momentum vector will align along the B2 vector. So previously it was at the angle 32.31 degree with B1 vector. So the angle between largest value of j for the largest values of total angular momentum number j and its z component jz and B1 vector, which is changed from B1 to B2, will be, we have to add that old angle, that is 32.31 degree, with the this angle, that is the angle between B1 and B2, that is 60 degree. So we'll get the new theta, that will be 60 degree plus 32.31 degree, that is 92.31 degree. So the value of theta in degree rounded off to the nearest integer is 92 degree. So the range of the answer will be 92 degree to 93 degree. So from the solution we found that the value of theta, that is the angle between the total angular momentum vector j and the magnetic field vector b vector, is either 92 degree or 93 degree, because it has a range from 92 degree to 93 degree. This question was asked in the GATE physics paper 2000, and this is a MCQ type question, and this question is from the topic quantum mechanics. The question is, a spin half particle with g greater than 0, that is Landé factor value is greater than 0, is subjected to a magnetic field H vector equals to H naught z cap. So the magnetic field vector is along z cap direction. If the quantization axis is along plus z cap, then the minimum energy eigenstate is given by, first option A is downspin state, option B is 1 by root 2 times upspin minus downspin, option C is upspin state, and the last option is 1 by root 2 times upspin plus downspin state. So you have to find the correct answer. The magnetic moment due to a spin half particle, let's say that is electron, is given by magnetic moment vector, that is mu s vector, equals to gs times e by 2m times s vector. Here s vector is the spin vector of the electron and gs is the Landé factor for the spin component. Now it is given in the question that the magnetic field is H vector equals to H naught z cap. So along the z cap direction. Now the Hamiltonian of the system is defined by minus mu dot H. So that is the energy, or Hamiltonian, due to the coupling between the magnetic moment and applied magnetic field. So the Hamiltonian of the system will be minus gs times e by 2m times S vector dot product with H naught Z cap. So it is the magnetic field given in the question. So we'll get the Hamiltonian for this system is minus H naught GS E by 2m Sz, because here we are getting dot product with S vector and Z cap. So it will give the projection of the S vector along Z cap direction. So that will give the Sz. It is given in the question also GS greater than 0. Now the eigenstate of the Hamiltonian is same as the eigenstate of the Sz. So the eigenstate of the Sz, that is the Z component of the spin, is either up spin or down spin with the eigenvalues h cut by 2 and minus h cut by 2 respectively. So up spin state will have the eigenvalue h cut by 2 and down spin state will have the eigenvalue minus h cut by 2. So for the down spin state, we have the eigenvalue for Sz is minus h cut by 2 and up spin state is h cut by 2. So if we put that eigenvalues of Hz for up spin state, then we will get the energy of the up spin state will be minus h naught gs times E h cut by 2m. And for the down spin state, the energy of the system will be E down equals to h naught gs E h cut by 2m. Now given in the question gs greater than 0, so clearly the energy for the up spin state is less than energy for the down spin state. So the minimum energy state is given by up spin in this question. So option C is the correct answer for this question. So according to our solution, the spin half particle with the Landis factor greater than 0 is subject to a magnetic field H vector equals to H naught Z cap. If the quantization axis is along Z cap, then the minimum energy eigenstate is given by the option C, that is up spin state. This question was asked in the GATE Physics paper 2000. This is a MCQ type question and the topic of the question is quantum mechanics. The question is, if a spin 1 particle is in the state m equals to 0 with respect to quantization axis n cap, which of the following is correct? Option A is expectation value of the spin vector, that is S vector, equals to 0. Option B, expectation value of the S vector is n cap. Option C, expectation value of the S vector is root 2 n cap, and the last option, option D, expectation value of the S vector is minus n cap. So we have to find the correct answer for this question. For a spin 1 particle, assume the quantization axis to be z axis. So the state of the particle is s equals to 1 and m is equals to 0. That will be a eigenstate of Sz operator. So here Sz operator is the z component of the spin of the particle. For an eigenstate of the operator Hz, we know the expectation value of Sx and expectation value of the Sy will be 0. This can be easily proved by considering the Sx in terms of the annihilation and creation operator, that is S plus and S minus operator. And if we take the expectation value of the S plus and S minus, then it will come to 0. Now the expectation value of the Hz operator is ms times h cut. So the expectation value of the S vector will be expectation value of the Sx along x cap plus expectation value of the Sy along y cap plus expectation value of the Sz along z cap. Now these two terms are 0 and expectation value of the Sz is ms h cut times z cap. So the expectation value of the S vector will be ms h cut z cap. Now for the particle state s equals to 1 and ms equals to 0, the expectation value of the spin vector, that is S vector, will be 0 because ms equals to 0 for this particle state. So option A is correct. So according to our calculation, we found that for the spin 1 particle in the state m equals to 0 with respect to the quantization axis n cap, the first option, that is the expectation value of the spin vector is 0 is the correct answer for this question. This question was asked in the GATE physics paper 2004. This is the MCQ type question and the topic of the question is quantum mechanics. The question is the Hamiltonian of a particle is given by H equals to p square by 2m plus a potential term that is V as a function of mod r plus phi as a function of mod r times L dot s. Here s is the spin of the particle, V as a function of mod of r and phi as a function of mod of r are potential functions and L vector is the r cross p, that is the angular momentum. The Hamiltonian does not commute with option A, that is L plus S, option B, that is S square, option C, that is Lz, and the last option D, L square. So we have to find which option or which term doesn't commute with the Hamiltonian of this system. So the Hamiltonian of the system is given by p square by 2m plus v as a function of mod r plus phi as a function of mod r times L dot s. Now we can write the total angular momentum vector for the particle or for the system is L plus S. So we'll take dot product on both sides. So we'll get j square equals to L square plus S square plus 2 L dot S. From here we can get L dot S in terms of J, L and S, that is half of J square minus L square minus S square. So we can write our Hamiltonian as p square by 2m plus v as a function of mod of r plus half of phi as a function of mod of r time j square minus L square minus S square. Now from the expression of the Hamiltonian for this system, we can say the eigenstate of the Hamiltonian will also be a eigenstate of J or J square, also L or L square, and also S and S square. So if two operator has the same eigenstate, then they will commute. So we can say from here H will commute with A square, H will commute with L square, and H will commute with L plus S, because H will commute with L as well as S. So the only thing, H will not commute with the Lz operator. So commutation of H and Lz will be non-zero. So Hamiltonian does not commute with Lz. So that is the option C is correct. So from the explanation, we found that the Hamiltonian of this system doesn't commute with option C, that is Lz. This question was asked in the GATE physics paper 2007. This is a question from the topic quantum mechanics and this is a MCQ type question. The question is three operators x, y and z satisfy the commutation relations, that is commutation of x and y is I h cut z, commutation of y comma z is I h cut x and commutation of z and x is I h cut y. The set of all possible eigenvalues of the z operator in units of h cut is option A 0, plus minus 1, plus minus 2, plus minus 3 and so on. Option B half, 1, 3 by 2, 2, 5 by 2 and so on. Option C 0, plus minus half, plus minus 1, plus minus 3 by 2, plus minus 2, plus minus 3 by 2. So this will be 5 by 2. There is a mistake in question and so on. And the last option minus half, plus half. So let us see which option is the correct for this question. Given that the commutation of x and y is I h cut z, commutation of y comma z is I h cut x, and the commutation of z and x is I h cut y. Since the component of total angular momentum j follow the above relation, that is jx, the commutation of jx and jy is I h cut jz, commutation of jy and jz is I h cut jx, and commutation of jz and jx is I h cut jy. So the z operator is behaving like jz, that is the z component of the total angular momentum, and it has the eigenvalues plus minus mj h cut, where mj has the values 0, comma plus minus half, comma plus minus 1, comma plus minus 3 by 2, comma plus minus 2, comma plus minus 5 by 2, and so on. So by this analogy we can say the eigenvalues for the z operator in terms of the h cut is 0, comma plus minus half, comma plus minus 1, comma plus minus 3 by 2, comma plus minus 2, comma plus minus 5 by 2, and so on. So our option C is correct for this question. So according to our solution, the set of all possible eigenvalues of the z operator in units of h cut is option C, that is 0, comma plus minus half, comma plus minus 1, comma plus minus 3 by 2, comma plus minus 2, comma plus minus 5 by 2, and so on. This question is from the GATE Physics paper 2008. This is a MCQ type question from the topic quantum mechanics. The question is, let the state phi naught denote the ground state of the hydrogen atom. Choose the correct statement from the options given below. So first option is the operator, that is commutation of Lx and Ly operating on the phi state will be 0. Option B, J square operating on phi naught state will be 0. Option C, L dot S operator operating on the phi naught state will be not equal to 0. And the last option, option D, that is the operator, that is the commutation of Sx and Sy operating on phi naught state will be 0. So let us see which option is correct. So the ground state of the hydrogen atom is denoted by the state phi naught. So the principal quantum numbers for the ground state will be n equals to 1, L equals to 0, and S will be either plus half or minus half. Now by solving the Schrodinger equation for the hydrogen atom, we can get the ground state of the hydrogen atom, that is 2 times 1 by a naught to the power 3 by 2 times e to the power r by a naught. Here a naught is the Bohr radius. So as we can see, the ground state of the hydrogen atom, the wave function is only function of the position, that is r. It doesn't depend on the angle theta or phi. So it is independent of the azimuthal angle phi. So here azimuthal angle phi is basically the angle in the xy plane. Now this operator, that is commutation of Lx and Ly operating on the phi naught state, it will give basically I h cut Lz operating on the phi naught state. Now in the spherical polar coordinate, that is r theta phi, we can represent the Lz operator as minus I h cut del del of phi. So we can write this operation, that is equal to h cut square times del del phi of this phi naught state. Now this state is independent of the angle phi, so it will give 0. So option A is correct. So as we can see, the first option, that is the this operator commutation of Lx and Ly operating in the phi naught state is giving 0. So we don't have to check the others option. So the first option is the correct answer for this question.